Have you ever really thought about how we get oil out of the ground? I mean, we're talking about pulling a liquid out of what seems like solid rock, thousands of feet down. It sounds totally impossible, right? Like trying to squeeze water from a stone. But here's the secret. That rock isn't as solid as it looks. It's actually filled with a hidden, microscopic network of pathways, a kind of secret superhighway that lets fluids move. Today, we're going to pull back the curtain and see how engineers map this incredible, invisible world.
So let's just start with that big question right there. How in the world does oil flow through something we use to build skyscrapers? It feels like it just shouldn't work. Well, the answer isn't magic. It's a fundamental property of the rock itself, something that scientists can actually measure, understand, and even predict.
And that property is called permeability. This is the key to the entire puzzle. You already know what this is intuitively. Think about a kitchen sponge. It's packed with all these interconnected holes, so water just zips right through it. That's super high permeability. Now think about a brick. It's dense, solid, there's pretty much nowhere for water to go. That's incredibly low permeability. The rocks we find oil in are somewhere in between, and figuring out exactly where they are on that scale is everything.
To get that crucial number, scientists don't start out in a messy, chaotic oil field. Nope, they go to the lab, where things are clean and controlled. They have a kind of rule book, a foundational equation that describes how fluids are supposed to move through any porous material. And that rule book is called Darcy's Law.
Okay, I know this looks like a scary math equation, but trust me, it's really just common sense dressed up in symbols. You've got Q, the flow rate, that's just how fast the liquid is moving. That speed depends on A, the size of the road, and delta P, which is basically the push behind the fluid. So what slows things down? Well, that's mu, the fluid's thickness. Think about how much easier it is to push water through a straw than honey. And finally, L, the distance it has to go. All these simple pieces help us find that one magic number we're looking for, permeability.
So here's how it plays out in a real lab. An engineer takes a little cylinder of rock, a core sample. They get a fluid with a viscosity they already know, in this case, a simple brine. They then apply a very specific amount of pressure to push that brine through the rock. And all they have to do is measure how fast it comes out the other side. They take all those numbers, plug them back into Darcy's Law, and boom, they've calculated the permeability for that one piece of rock.
But, and this is a huge but, there's a catch. For that test to be valid, they have to follow some really strict golden rules. The flow has to be nice and smooth, the fluid can't have any weird chemical reactions with the rock, and, most importantly, you can only have one fluid in there filling up 100% of the space. The number you get from this perfect, pristine, idealized test, that's called absolute permeability. It's our best-case scenario number.
And that brings us to the single biggest headache for a reservoir engineer. How do you take that perfect number from one tiny piece of rock in a sterile lab and use it to understand a massive, messy, ridiculously complex oil reservoir that's miles underground?
Because, let's be real, these two worlds could not be more different. In the lab, your fluid is flowing in a nice, neat, straight line. In a real reservoir, it's flowing in from all directions, radially, towards the well. In the lab, you have a small, uniform plug of rock. The reservoir, it's a huge, wildly varied geological formation. The lab uses one pure fluid. The reservoir is a chaotic soup of oil, water, and gas, all sloshing around together. The gap between the lab and reality is just enormous.
And because of that gap, the lab samples can be flat out deceiving. I mean, that little core you tested? It might have come from a super permeable sweet spot that doesn't represent the tighter rock all around it. The very act of drilling and bringing the core to the surface can damage its delicate internal structure. And there's always a human temptation to pick the best-looking rock cores to test, which might not be representative at all. It's like trying to understand an entire city by just studying a single perfect-looking brick. It just doesn't work.
So if you can't trust a single measurement, what do? You get clever. This is where engineering becomes an art form. They've developed brilliant ways to take all these different measurements from a messy reservoir and calculate a single, useful average permeability that actually represents the whole system.
I mean, the whole idea of a perfectly uniform reservoir, just one consistent type of rock stretching for miles, it's pretty much a fantasy. As the source material puts it so well, it is rare to encounter a homogeneous reservoir in actual practice. You're always dealing with a mix of different layers and types of rock. So averaging isn't just helpful, it's absolutely necessary.
One of the go-to methods is a weighted average. This is perfect for layered rock. I want you to picture a layer cake. You've got a spongy vanilla layer, then a dense, fudgy chocolate layer, then another spongy one. If you pour milk over the top, where is most of it going to flow? Through the spongy layers, right? A weighted average does the exact same thing with math. It gives more importance, or weight, to those high-flow, super permeable layers.
But what if the flow has to go through one type of rock to get to the next? Like a chain. For that, you need a harmonic average. The best analogy is a train. It doesn't matter if you have a bullet train engine and a bunch of high-speed cars. If one of the cars in the middle has square wheels, the whole train is going to move at a crawl. That slow car is the bottleneck. It's the same in a reservoir. If oil has to get through a block of really tight, low permeability rock, that block controls the flow for the whole system.
Okay, so we've covered the rock itself, the different layers, the fluids, but there is one more gigantic factor that changes the entire game: pressure. Miles underground, that rock is being squeezed by an almost unimaginable force from the weight of everything sitting on top of it, and that changes everything.
And just to give you an idea of what we're talking about, for every single foot of depth, the pressure increases by about 1 pound per square inch. So if your reservoir is, say, 10,000 feet deep, you're looking at 10,000 psi of pressure constantly squeezing down on that rock. It's an absolutely immense force.
Now that rock isn't just getting squeezed from the outside by this overburden pressure. The fluids inside the pores, the oil and water, are also under pressure and they're pushing back. It's kind of like the air in a tire holding it up from the inside. But what happens when we start pumping oil out? We start letting the air out of the tire. We're reducing that internal support system.
And here's the effect. With less pushback from the inside, that massive overburden pressure from above starts to win. It literally compresses the reservoir, squeezing the individual rock grains closer together. And what's the first thing to get squished? The empty spaces in between them. The pores, the pathways, our secret superhighways, they start to shrink.
And you can see that effect so clearly right here. The actual solid rock grains themselves, they don't compress that much. They're pretty tough. But the pore volume, the empty space, is way, way more compressible. It gets squeezed shut much more easily. So what does that mean? It means as we produce oil and the internal pressure drops, the permeability of the rock itself actually goes down. The superhighway literally gets smaller, making it harder and harder to get the rest of the oil out.
So a reservoir isn't some static, unchanging box of oil. It's a dynamic, living system that changes and evolves as we interact with it. And that leaves us with a really critical question. If the very pathways for oil are constantly changing and shrinking under pressure, how can we possibly build models that are accurate enough to predict the future of our energy resources? Answering that question is one of the biggest challenges that will define energy production for years to come.